Hello everyone, I'm Dr. Hussein Haydari, and today we're going to continue our discussion on polymers. So far, and during the course of the first week, we've looked at polymer chemistry, we've looked at the structural features of these polymers. We saw how these side groups could affect and influence the basic properties of these polymers. We've looked at the distinct behaviors of different types of polymers. And we've tried to systematically look at that through the course of this week. Specifically, we've been looking at mechanical properties and the stress-strain behavior. We classified these different polymers in terms of their brittleness. And so I'm going to pick up where we left last time and continue that discussion in a bit more depth today. So this was the last, or probably both the first and last figure that we started with, ended on last lecture. What it shows is the stress-strain behavior of different types of polymers. So polymers could have a brittle behavior all the way to an elastomeric behavior, and in between there's this plastic behavior. What is different is the elongation as well as the failure. You can see that the brittle polymers, they do not experience that sort of extended elongation period that plastic polymers have, or the elastomers, and they actually go through this slope of increased stress until they reach the point of failure. Unlike brittle polymers, and we talked about why this is, plastic polymers have this distinct behavior where they reach this point at which they achieve their ultimate stress level, and beyond that point it kind of plateaus all the way to failure, and they have relatively high elongation values. And similarly for elastomers, they have the same, but they don't have that sort of necking behavior here. So you can see that they've got a rather distinct behavior in terms of the mechanics of these different types of materials. And yeah, we already discussed why this happens with respect to their chain structure, their crystallinity, and why the alignment of those amorphous regions actually induces this sort of a special behavior here in plastics. Today we're going to look at the main processes that govern polymers and how we can actually utilize this change of mechanical behavior to modify polymers. So the first thing we're going to look at is the effective temperature and strain rate on this mechanical behavior. So it's very interesting that polymers have a dependency on temperature when it comes to their stress-strain behavior. Now, what you see here is that as we reduce the temperature, and you've probably heard of a lot of examples of engineered systems failing at lower temperatures. The reason is that this stress-strain curve here completely changes as you cool the material down. What you see is it goes from a ductile behavior to more of a brittle behavior. Now, apart from just the point of, reduced or decreased elongation, you also have an increased slope, which you can see corresponds to elastic modulus. So typically it becomes stiffer, it becomes stronger in terms of the strength, the mechanical strength, the ultimate tensile strength increasing, but it has a lowered level or a decrease in elongation, as you can see when you reduce the temperature. So basically it moves from a ductile behavior to a brittle behavior. So apart from just looking at the structure of your material, you can look at the temperature at which it's experiencing to actually predict some of its mechanical behavior. It's not just a single variable sort of output, this stress-strain behavior. It's a multivariable, and it is dependent also on temperatures, you can see. Another factor influencing the behavior of the material is the strain rate. So how fast you apply this deformation, or this elongation in this case, is really important. As you increase the strain rate, what happens is that you actually have the same effects as if you were decreasing the temperature. So it becomes more brittle. So if you apply a very fast, sort of similar to, not exactly what an impact is, but if you actually reduce the time span of what your deformation applied to is happening through, it is going to influence the brittleness of the material. It's sort of a, you can imagine an equivalent to making the material more brittle as you apply the force or the strain in a faster, higher rate. So this isn't the major focus for today's lecture. Today's lecture, we're going to actually look at the effect of temperatures, but from a different viewpoint. So just to really start from the foundations, we have three main phenomena that actually happen in polymers. The first is crystallization, which you're already familiar with. So we discussed how in polymers, when they start the polymerization reaction, you have nucleation sites that locally start the chain reaction, and then it propagates into these spherulite sort of grains. And what happens is that at some point these different nucleation sites propagate and meet each other at these boundaries, as you have this granular structure that you can see here. So this we've already seen, and we've seen how the growth from the nucleus all the way to boundaries can happen and propagate through these crystalline structures, and in between there is these intermediate sort of amorphous regions, and this is basically the crystallization process. Now, if you basically look at the reverse of this, which is if you heat up the material to actually start melting it, that would be when these crystals dissolve into monomers. So the interesting thing here, which makes it really special, is that it doesn't always happen like that. Unlike a lot of the other materials that if you reverse the solidification, could be crystallization. In the case of polymers, it's crystallization. You achieve melting. Here you can actually get two distinct types of behavior. You can have melting or a glass transition. Now, how do these differ? Well, glass transition kind of gives away what it is in the name. It basically transitions into glass. So what it means is that it gets to this glassy, brittle behavior. Now, let's look at how the material changes as you cool the material down. So if it was just a regular condition, it would crystallize into a solid. But when you have a material that has glass transition, that's going to be different. Now, let's first look at the case where you have crystallization. So crystallization here, what you see is that, first of all, it depends on the temperature. We already discussed this. At different temperatures, if you give the material time, these crystals will grow, and it's always going to be the sort of an S-shaped curve where you go from 0% crystallinity all the way to 100%. I've already told you that this is really difficult to achieve, and you can see that this kind of plateaus here, asymptotes, as if it really doesn't reach there. But basically what happens is that there's a phase where the slope changes and then it goes down again. But depending on what temperature you have, the time span of this crystallization can significantly change. This is a logarithmic scale plot. So here it can take thousands of minutes at an elevated temperature. If you reduce the temperature to a cooler temperature, the crystallization can happen much faster. And that's clearly because it becomes more packed, dense, and the material mobility is reduced because the molecules can't move around as much. So you're actually helping the crystallization process. When you heat it up, you've got more kinetic energy and thermal energy basically from the motion of molecules. And so to crystallize and form a solid, it's going to take even longer. Now, the question really is, how do melting and glass transition differ? And here's to understand that. So the way we actually measure these, and in general measure the behavior of material, is we increase the temperature and we look at how density changes. The inverse of density is the specific volume. So that's 1 over density. Basically, what we look at is when we see a shift in the behavior of the material, okay? So this is a phase diagram. What you see here is that you can see that as we increase the temperature, the material has actually a decrease in density or an increase in specific volume. So again, the specific volume here is 1 over density. So when it increases, you know that the density is actually decreasing. So when the material is solid, the distinct behavior, the distinct characteristic is density is going to be really high, in which case specific volume is really low. As you melt it, suddenly with a typical material, you should see a shift when it goes from solid to liquid, where the density here actually decreases significantly because the molecules, of course, have gotten far apart, and so it's become a liquid. But with these special types of materials, semi-crystalline or amorphous materials that have this glassy behavior, you see a two-step process. It doesn't all happen at once from solid to liquid. It goes from solid to sort of a rubbery material here, sort of a viscous, slurry type of material, and that continues on to get heated up more and more until it reaches a very thin liquid. So the distinct behavior here is that you have two different points of change of slope. So what you see here is this happens a lot earlier, then continues on. And so what you see is that when it reaches the glass transition temperature, it goes from a brittle material into this sort of a flexible, I would say rubbery material, and then it liquefies. So you've probably seen this with a lot of plastics around you. If you put them inside the freezer and then you take them out, you try and snap it, it breaks with a really sharp and brittle break. Whereas if you heat them up and then you try deforming it, it doesn't actually break and fail like that. It can actually withstand some level of deformation. And that's exactly how the temperature here, the glass transition temperature, influences the behavior of the same material. It can go from brittle to ductile, basically. And that is only if you control whether it's before or after glass transition temperature. Now, another diagram, another phase diagram here, can show you exactly what I explained here. So some materials, when you heat them up, if I select a material with a specific molecular weight here, of course, as the molecular weight here, you can see it's crystalline. You have a different regime here, which is partially crystalline, and if you have it over here, it will be amorphous, right? So these crystalline solids have the highest molecular weight. So actually, molecular weight here is maximum. So this axis here starts from maximum here to a minimum. It goes reverse. And so if you have a partially crystalline, it's going to have a lower molecular weight, and amorphous, which would be right here, would have the lowest. But basically, when you've got a crystalline solid and you heat it up, it has a very similar behavior to a metal. You remember the network polymers. They have a very similar behavior to metals. As you increase the temperature, what happens is that it goes through a phase change into a liquid. It doesn't go through this intermediate state here into a rubbery state, it rather goes through a phase change immediately to a liquid. So the way you actually look at these phase diagrams is you look at, if you pick a cross section here and you increase temperature, how it goes from this region, it's still a solid, it reaches this temperature, and then beyond that, it melts. This entire region is molten. If you had it here, it would melt into a viscous liquid after this particular temperature. But if you have this material here, which is a semi-crystalline material, it melts into this sort of a viscous, but yet still tough and impact resistant material. And then it continues on to a sort of a rubbery material. And then if you continue, it's going to thin out into a really liquid sort of solution. So this is rather difficult to understand at first sight, but if we just look at it with more time and attention, you actually start seeing all the details showing up. Another thing you can get from this plot is that if you actually change molecular weight, you're going to get a change in the glass transition temperature and the melting temperature. So again, the glass transition temperature is always lower than the melting temperature. But what happens is that it changes with molecular weight. Now, this is a really important behavior. And in a minute, I'll tell you why it makes polymers even more special. Before we get there, let's take a look at what other things influence the melting and glass transition temperatures. Another very important factor is the chain stiffness. Now, what do I mean by chain stiffness? You remember from the early lectures of the first week, we discussed how conformation can change. We discussed how these chains could be really rigid if you've got a double bond, for instance, and therefore shifting its shape or deforming it could be really hard. Whereas the chain stiffness could be really low if they're all single bonds, and if the material has that sort of ability to change its conformation pretty easily. So it's interesting to know that as the chain stiffens, you actually have an increased melting and glass transition temperature. This probably also intuitively makes sense. But just to remember what we discussed previously, if you want to increase your chain stiffness, you can either add your side groups, make them, you remember how replacing a hydrogen with a larger side group, a CH3 or even a ring, could actually significantly influence its mobility and could affect its ability to move and rotate around that bond. Similarly, adding polar groups and side groups that interact with each other and enforce these basically magnetic force fields onto each other can also reduce the mobility. And of course, the double bonds, and I already mentioned the aromatic chain groups that could be either on the side groups or in the main chain. These all add to the stiffness of your chain. So it takes the chain from a really flexible one to one that's rather rigid and stiff to move around. So, and as you increase the chain stiffness, what happens is, of course, you have an increase in the melt and glass transition temperature, meaning that you need to have a higher temperature, a larger amount of thermal energy to be able to actually liquefy or turn it into a rubbery material. Interestingly as well, it's also a function of impurity. As you have more and more impurities, you get a lowered melt and glass transition temperature. What that means is that impurities help your liquefaction or the melting process. Again, the reason for that is that impurities act as sites for sort of a reverse nucleation of the melting process. So they actually already add to the mobility of the material. So when you're heating it up, trying to melt it down, the impurities help you melt it down easier, rather than if it didn't have any impurities and if it was a perfect crystalline structure, very nice bonds there. Without any imperfections, it would be really difficult to melt it down and perturb that structure. Now, here I've included from the book some of the, again, frequently used polymers that we already looked at before. And I've included their glass transition and melting temperatures. So you can see that all these materials do have both a glass transition temperature and a melting temperature. So you can see that none of them are crystalline, like what we had last time, which was phenol formaldehyde as network crystalline solid. We haven't actually included it here, but what you have here is that all these materials have a glass transition temperature and melting temperature. Now, this part is really important because this actually gives you a view of all the materials around you that you see in daily life, all the materials that you will be using in your applications in your future careers. How do they perform under different temperature conditions? So this has been the reason for the failure of a lot of the engineered systems around us. You probably heard of lots of failures in the space programs, lots of failures in the naval programs, but this has always contributed to that because there has been a lack of information in terms of the change of the performance, the mechanical performance of polymers as a function of temperature. Now, this is where it gets really interesting. We are at room temperature right now, and you can see that a lot of the materials at room temperature are glassy, meaning that room temperature is below their glass transition temperature, okay? So if you heat, for instance, nylon or polyester up to 57 or 69, respectively, you will hit that glass transition temperature and it will become more flexible. It will become easier to deform. At the moment, it's rather brittle, okay? So you can see that a lot of these materials are brittle at room temperature. They're glassy, right? If you heat them up to their glass transition temperature, now they become deformable. If you heat them up to their melting temperature, now they become a liquid. So in between here is a good region to deform them, right? A lot of these materials at room temperature, they're already deformable. So they won't break like glass. They're not glassy because their glass transition is negative here. You can see it's negative 110, negative 97. So at room temperature, polyethylene, polypropylene, they're all going to be rather deformable. Now, if you pick a piece of polyvinyl chloride, PVC, you'll see that at room temperature, it's below its glass transition, so it can snap and break quite easily. So that's why this information here is really important. You know when these materials melt into a liquid, but furthermore, you know when they actually transition from a brittle glassy material to a deformable plasticky material. And this is why now you can look around you in the room, at your home or the office, or when you come to the lab and try and experiment and process these plastics and polymers, you'll know at this certain temperature whether they're brittle or ductile. And you'll know exactly what's the best operating temperature if you want to change their shape. If you've got, for instance, a thermoplastic and you want to deform it, you know what temperature to pick. So again, the reason why these distinct temperatures are observed is because of the structure. So again, a lot of these that have a rather high melting temperature, like 265 for nylon and polyester, it's because they have a really strong structure. If you look at nylon and polyester, if I can find it here, you can see that, for instance, here, nylon and polyester have a lot of stuff going on here, right? You can see all these polar groups. You can see the aromatic ring in the backbone. You can see how strong this is in comparison with, for instance, polyethylene. Now, of course, if you look at the temperature that polyethylene melts, it's 115. because it's got a very simple C2H4 monomer in its backbone. And that is the reason why the strength of the backbone, the strength of the chain, can significantly influence the melt and glass transition temperatures. So now what I'd like to ask you to do is to go and look at this table again, go and look around you and try and see all the examples of how this glassy versus ductile behavior as a function of temperature, first of all, ties in the structural features of these into their mechanical properties, but also in general, what sort of material would you pick if you were to, for instance, 3D print an object and you only had access to lower temperatures? And so this is why, as we move towards the rather exciting part of these lectures, all of this is pretty exciting, but when we get to processing and manufacturing objects with these polymers, you will see how all of these structural and mechanical temperature-dependent behaviors all come into play to tell us exactly what configuration to use when we're manufacturing an object. And we're going to get there pretty soon. So for now, I'm going to leave it there. Maybe I'll talk a little bit about this one last slide, and then we'll leave it there and continue the discussion in the next lecture. So what this slide is showing is that this is already what I showed you. Molecular weight can actually influence the melt and glass transition temperature. But another thing here is, as I told you, the impurities. Similarly, the availability of the side group can influence the temperatures to the melt and glass transition temperatures. Now, what happens is that if you increase the branches, you know that it increases your strength, but it actually decreases impurities and branches, both decrease your temperatures, melt and glass transition. So what can we tell here? This is another very important point, and that is we've already seen this plot. What did it show us? What it told us is that polymers are rather polydispersed. You have a distribution of lots of different chain lengths, lots of different densities of branches, lots of different molecular weights. So if you have a distribution, you can imagine that each region of your material is going to have a different melt temperature and a different glass transition temperature. So what's going to happen here is that your melting in your glass transition isn't going to happen at a specific temperature. It's going to be a mixture of these, and it's going to happen over a range of temperatures, because in some regions of your polymers, you've got lower molecular weight, some regions you've got higher molecular weight, some regions you've got more branching, you've got maybe a little bit more crystallinity, some regions you've got less crystallinity. So that's why, because it's polydispersed, in other words, it's got different regions with different sort of structural features, you get a very distinct melting behavior. And so melting and glass transition don't happen at a particular temperature, they happen over a range of temperatures. So maybe if you've got this material here, for instance, polyethylene, and it tells you the melting temperature is 115, and then high density polyethylene is 137, it's actually going to be somewhere from 110 to 140, that depending on the density, depending on the molecular weight, depending on the crystallinity, this material is going to transition from a solid to a liquid. So that's why these materials, polymers in general, are really exciting materials. You can basically utilize these special behaviors, and people have already, to get some really nice applications going. And we will be talking about that moving towards next week. But for now, I'm going to leave it at this slide. I'm going to leave it for you guys to think about how that sort of a crystalline amorphous mixture, that sort of a molecular weight distribution that always happens in polymers, actually induces this range of change of properties, and also think about different polymers around you and how they perform. And we will continue this discussion in the next lecture. Have a wonderful day.